All right, it's 10 o'clock. Let's get started. Good morning, everybody. Welcome to the 17th edition of the Long Coffee Break. My name is Joshua Likes. I'm a sales engineer with Long Building Technologies. With me today is Eric Van Tome from Pennbarry. We're going to discuss laboratory exhaust fans. Eric, take it away.
Hey, thanks, Josh. I appreciate you inviting me and Pennbarry to participate in the Long Coffee Break. I love the concept and definitely share that with some of our other customers. So let me go ahead and share my screen here. And it should be coming up for you here. Just let me know when you can see it.
Yep.
Okay, great. Well, let's jump right in. I had this technical difficulty earlier where it didn't want to click to the next slide. There we go. So real briefly, we'll cover kind of the learning objectives. So we're going to talk briefly about the typical applications, high velocity versus induced flow fans, some plume development, touch on sound, as well as some material and coating considerations and motors and actuators that are typically used. I do want to spend just a minute talking about rain mitigation as it relates to lab exhaust fans from a design perspective. And then we'll touch on redundancy and some new tech, some variable nested nozzle technology coming out by Pennbarry here. So we'll touch briefly on two different types of laboratory exhaust fans. You've got kind of two options: the physical stack, which is kind of the traditional style where you've got a house centrifugal blower mounted on the roof, or maybe down in a penthouse just below. And then a physical stack. It's a built-up system. Typically, that stack is pretty tall, and so you're going to have guy wires tied back to the roof deck. Typically, is going to create kind of an unsightly look, but is effective for exhausting laboratory exhaust fumes. Something that's been newer and popularized here by fan manufacturers over the last probably 15 to 20 years or so is really the virtual stack. And so this is still a fan mounted on the roof. Typically the minimum physical height is about 10 feet. And then you get a virtual stack because of the high velocity nature of the exhaust produced by the fan itself. It's a very simple installation. You don't typically have any guy wires, and you have a very nice, neat, clean roof line. Typical applications, we see these quite a bit in universities and schools, hospitals, research facilities and laboratories. We've even started to see some of these in the wastewater treatment facilities. We've even done some for emergency generator exhaust, as well as odor control applications. The typical nozzle types that we have and that are pretty popular in the industry, there's really two. One being the high velocity, this is quite simply a narrowing of the discharge of the fan. And what that does is accelerates the air and creates a virtual stack or a plume. There's also an induced flow style. And this is actually one that AMCA, our trade association, has gone ahead and created a certified ratings program for, because in a typical fan performance, you're going to measure this inlet flow and you can measure this outlet pretty easily. But this induced flow here, use my laser pointer here, shown by this green arrow here, this induced flow is a little bit more difficult to measure. And so AMCA went ahead and created a certified ratings program. I'll show that on the next couple of slides here. It is additive, but it's difficult to measure this. And so what AMCA did is came up with a certified ratings program. I'll talk about the testing in the next slide here, but essentially it's 10,000 CFM coming through here, and you have 7,000 coming through the induced flow area of the fan. You get 17,000 CFM coming out. I should mention that, so not all manufacturers participate in this certified ratings program. This is voluntary. And so when you're selecting and choosing lab exhaust fans, make sure that if you're looking for one that's got this induced flow capability, be sure you're looking for this AMCA certified ratings program label for specifically for induced flow. This is really just a schematic of what the AMCA 260 test procedure looks like. You've got your induced flow fan blowing into the chamber in a variable resistance box. So what they're doing is they're really measuring the inlet flow, and they're measuring the outlet flow, and then really subtracting to come up with whatever that induced flow is on the certified ratings program. Plume Rise. So Plume Rise is a very common and a typical resultant criteria that is produced by the fan manufacturers. If you have a physical stack, it's very easy to measure what that is, and you know what your plume is, or you know what your physical stack height is going to be. But if you're going to use a virtual stack method for a laboratory exhaust fan system, it's a little bit more difficult to measure, okay, what is that height here? So the ASHRAE Laboratory Design Guide and the HVAC Handbook for applications has really two different methods for calculating what this plume rise is. And each manufacturer kind of uses their own or can produce both. We can produce both as part of our resultant submittal data, but they either use this momentum equation or this Briggs equation. Both are fairly common and have been ASHRAE tested and approved, and so both are utilized in producing and comparing one lab fan to another. Talk real briefly about plume dispersion. I briefly mentioned it before. One of the fan applications is generator exhaust. So depending on the proximity of the generator to the laboratory fan, you may have a high temperature situation there. So that high temperature exhaust airstream may result in a lower plume rise due to some stratification, and that stratification, the amount of that and the angle of the plume is going to vary depending on that temperature. You also have sound considerations. So we've started to see many municipalities coming out with their own fan sound or equipment sound requirements at the property line. So one of the things when you reduce the outlet area of a fan and increase that velocity, you're also, one of the drawbacks to that is you're going to increase the overall fan sound, and so that can be an important criteria when considering which fan style, whether you're going to go with a high plume style or a regular power of ventilator style fan. And so you're going to have some sound metrics that are going to incorporate this outlet area, as well as some of the breakup motor noise and the fan noise. And then you're also going to have some sound coming through this bypass damper. So there's a number of criteria to consider from a sound perspective, and all of our submittal documentation can help you compare, one fan selection versus another. Coatings and special materials. So all of our fans are produced out of mild steel as a standard, and then we apply one of a variety of coatings depending on the application. We've got a little chart here at the bottom that kind of shows the typical corrosion resistance for the different coatings that we offer. But we also do aluminum, do fans out of these, we can do these lab fans out of aluminum. And we usually incorporate spark type B construction to help produce, create a spark resistant construction so that you're not dealing with any of that. So we have that available. We also can build fans out of stainless steel. Some manufacturers get into fiberglass. We do not, but that is also a typical material for laboratory exhaust fans. Our typical coating is a zinc-rich epoxy primer with a UV top coat. So all of these fans are typically mounted outdoors. So you're going to have some sort of UV protection included as part of the coating. Motors and actuators. So these are additional components. They're buyouts for us. We don't manufacture them, but we do utilize them as part of the fan construction. The motor is obviously driving the fan impeller, which creates the airflow and ultimately the outlet velocities. We get into the different types of enclosures, ODP, EFC, explosion proof, depending on what your application is. Same thing with the actuators, typical NEMA 2, NEMA 4X, and NEMA 7.9. I want to pause here just briefly to talk about rain and lab fans. So there's a couple of things that really need to be taken into consideration when utilizing lab exhaust fans, especially this inline style. There are some house centrifugal style lab fans that can mitigate rain a little bit differently, but specifically with these inline styles, these are all open air. There's no damper on the outlet of the fan that's going to shut off 100% of the rain coming into the fan. And because of that, rain can actually make its way down in through the fan, especially when it's shut off for maintenance or replacement, or if you have an N+1, which we'll talk about redundancy in a second here. If you have an N+1 type application where you've got some staging and you've got one fan shut down for a period of time, rain can actually make its way through the fan down into the ductwork and ultimately down into the building space if certain mitigation is not taken. So there's really two ways to handle this with this inline style fan. One would be installing drains in the ductwork, which is pretty common. We've seen that quite a bit to capture the rain in the ductwork and then run drains off of that so it doesn't get down into the space. Another way is where we have these mixing boxes. So Pennbarry can supply these mixing boxes, which are typically used for common plenum applications. But utilizing a side intake on the mixing box, which really what that requires is a duct penetration through the roof next to the fan, and then an elbow into the mixing box. Then we would put in a solid bottom to the mixing box, and then have a drain coming off of that mixing box as well. So those are really two common methods, and this is a really important aspect to take into consideration when designing a laboratory exhaust fan system. I mentioned it on the previous slide a little bit, but we do build common plenums where you can install multiple fans on the same plenum mixing box. This gives you greater flexibility for staging and energy control, and that N+1 type redundancy that I mentioned before. This also gives you the ability to utilize multiple smaller fans instead of just one larger fan. Now there is a little bit of an efficiency trade-off anytime you're talking about smaller fans versus larger fans. Larger fans are always more efficient than smaller fans. But when staging and energy control are of utmost priority, you may trade off individual fan efficiency for the overall system efficiency and flexibility from a staging and energy control standpoint. One of the most unique features we came out with us about 12 to 16 months ago or so is this is on our high velocity called our V-Plume style fan. We've created something that allows the user to adjust the outlet area of the fan as they reduce the fan speed. So again, more for energy control, users may want to reduce the fan speed a little bit for that energy control standpoint. And we allow you to adjust the outlet area so you can maintain a consistent velocity. We call this our VNN technology. And one thing I just wanted to highlight real briefly here is there's going to be, with any of these styles, there's going to be some components that are potentially exposed to the weather and the elements. And all of our components are mounted actually down inside the nozzle and fan system itself, so they stay protected from the elements. Our competition has a similar design, but it's actually got these two damper blades. And as those modulate back and forth, they can be bound up with, especially in climates where you have snow and ice to deal with. This is a slide that kind of shows, kind of rounds out our entire family of lab fans. As I mentioned before, we have our V-Plume. This is our high velocity style, up to 40-inch diameter wheels. Most of our testing is showing 15 to 20% more efficient than our competition. We also go over to our AMCA 260 certified induced flow fan. We offer this in a belt drive or direct drive configuration up to 44-inch diameter. And then two ancillary controls features that I mentioned that gives you greater flexibility and for staging and energy control is the variable nested technology that I mentioned on the previous slide, as well as then some lab exhaust fan controls. These are all available through Pennbarry. So if you have any further questions, some of the slides that we talked about here today are excerpts from a longer ASHRAE presentation where we dive deeper into some of the technical topics. So if you want us to dive a little deeper in any of that, please get a hold of your long salesman. And we'd be happy to come out and help or do another Zoom call like this. Thanks a lot again, Josh, for inviting me to participate, and hope this was informational for everyone.
Awesome. Thanks, Eric. Really appreciate that. Please tune in next week with Nick Bryant discussing the Valiant RTUs presentation. And as usual, please contact your lawn salesman if you have any questions. So thank you very much, everybody.